Okay. Thank you very much for kind invitation. And I will speak about one discrete analog of a linear differential model with delay and about the Mach number dynamics and its solution. So, discrete equations are results of discretizing differential equations, and the well-known algorithm used by numerical methods as Euler and Runge-Kutta others are examples of discrete equations. Such discrete equations can be solved step-by-step method. That is, the next value of the solution is calculated from the one of several preceding ones. Nevertheless, whenever exact formulas can be used to describe solution of discrete equations, this is preferred in computations because in addition to quantitative properties of solutions, also qualitative ones can be predicted. And we refer, for example, to the book by Elidi. We will demonstrate this using a discrete model arising from a discretization of a system of differential equations with single delay to find formulas for the solutions of the discrete systems derives. In principle, such formulas make it possible to solve even some special problems, such as how the process described by a given system can be controlled when it is stable or unstable, whether the coordinates of solutions remains positive, and others. So, for the basic notions, I refer to books that are written here with overviews and new results related to fractional linear systems, minimum energy control for fractional order discrete systems, and controllability of dynamical systems. And in papers here by Bartoševič, Kačorek, Sajewski, Klamka, Niezabitovsky, and Mozirska, Pavluševič, and Virvas, control systems and controllability are considered, while papers that I write here by Fečkan, Wang, Mazanti, Medina, Young, and Fečkan and Wang are considered problems of relative controllability and stabilization to discrete and discrete equations. And papers here are concerned with H-infinity control for discrete systems and finite time stability. But to be more concrete, the papers by Manitius, the following two papers, and the books by Huku and Kim and Ivanov consider a wind tunnel differential model with a delay, and this model is here. This is system 1 to 3 differential system of differential equations with delay h, and with a control functions. Of course, for details for values of coefficients a, c, w, delay h, parameter xi, I refer to papers by Manitius as well as for initial data. So, and now I will say a little about discretization of this system. This system is differential one, but it is possible to solve it by a discretization process. And because this system with delay is very specific, it is so-called system with weak delay, then recently my PhD student defend PhD thesis, Safarik, about such systems. So, and we will solve the system which arise after discretization. So, some words about weakly delayed systems. Consider system 6. This is system 3 of 3 equations. Matrices A, B are 3 by 3 matrices. Non-zero determinant of A, B is non-zero matrix, F is a given function, and I refer to this PhD thesis and to one of our previous paper. We defined a weak delay or weakly delayed systems as follows. Consider homogeneous system and system where the matrix B is omitted, is path to 0. And we define by a classical way by quasi-characteristic polynomial for equation 8 and characteristic polynomial for non-delay system 9. And now we say that system 8 is called weakly delayed if both determinants are the same, and this equality is valid for every lambda to be complex but not 0, because 0 is not possible to put in this D sub 1. Okay. This property was described in papers which I mentioned, and now I will focus your attention to discretization of the process. The derivative is discretized by very simple formula which looks like this. Epsilon should be very small positive number, and because this initial system is delayed systems, we should put epsilon such that we get this number m to be whole number, and then instead of the differential system we can consider a discrete one, and of course we can determine initial value for such system, and this is done here. So, system 1113 can be transformed by transformation which are written here into a system. This is discrete system with a delay, and delay is represented by the number m or m sub epsilon. So, initial data taken from the previous differential system are the following, and system can be written as follows here with matrices A1 and B1, and this control function which is given by this formula. So, if we consider eigenvalues of the matrix A1, we can see that if epsilon, it means the discretization is small, then eigenvalues belong to this interval for such range of epsilon, and to this domain if epsilon is less than this constant. So, and therefore we will assume that one of conditions is valid, and therefore we put epsilon equals to this number, and then all is okay, because eigenvalues by absolute value are less than 1, and we can expect asymptotic stability of the process. So, and now how to solve this delayed system? We solve it through a substitution which from delay system give us a non-delayed system, and substitutions are written here. Of course, there is a specific, this process is a little bit specific because only one dependent variable contains delay, and our substitutions are developed with respect to this fact. So, and now, after such transformation, we get a new system without delay in right-hand side, and matrices matrix A1 is as follows, a little bit complicated. So, and initial data can be derived from previous one. And now we are solving this high-dimensional system using transformation, which transforms the matrix A1 to the matrix A sub 2, which will have Jordan form. And in our case, it is necessary to consider not only algebraic multiplicity, but also geometric multiplicity of the zero root of this matrix. And because by known algebraic properties, geometric multiplicity of zero numbers of both matrices, the previous one A1 and A2 are the same and equals 1, then the Jordan form for matrix A1 can be determined easily, and this Jordan form looks like follows. And now it is easy to find solution of this discrete system, because powers of matrix A2 can be found very simple, and by formula from the book LID we can find solution of this discrete non-delayed system. And this is done by formula 38, where discrete system has such solution. And looking for several first values, we can say that after k equals 3, formula for solution can be simplified as follows. So, and if k equals or greater 4, then formula or the main part of formula takes very simple form. So, it means we are able to solve such discrete systems. And going back to variables x by substitution, which is used here, we get solution by this formula 44. So, and solution of discrete system and formula solution of discrete system is given in following theorem. For value x at for time to be epsilon equals this, for 2 epsilon equals this, for k equals 3 epsilon is given by this formula, and for more greater k, the formula looks like this one. So, of course, initial data it is possible to find from initial system. So, and now some words about this transform matrix. The transform matrix who transforms the matrix A1 to A2 to Jordan form has the following form. It can be found very easily by method of eigenvectors, no problem. And inverse matrix, which was found by MATLAB software, is the following one. There are 2 columns which are more complicated, and such 2 columns are written like here. This is second column and third one. So it means the solution of the problem is given, and it is expressed by formula which is written here. It means we going back to initial to previous dependent variables W. So what about comments? It means some theory about weakly delayed systems was given in sources here. in a recent paper from a conference ITSNAM, this problem is solved, but not so good way. Now we present more simple way. So, and results can be used and applied for solving of some control problems. I refer, for example, to our papers with Kristina Mensakova, which was published in this journal. So, and for new formulas, how to derive it, I can refer, for example, to the papers by Mahmudov. So, and that is all. And thank you very much for your attention.